Okay, hi guys. This is part 2 of Unit 2 for Precalculus, which is on inverses of functions. So first of all, what even is an inverse? So the inverse of a function is, put shortly, the function that reverses it. So in other words, if f of x is the inverse of g of x, right, f of g of x is equal to x. So we can see that's kind of wordy. So let's use our visual representation here. If we put some input in here, right? If we put some input into function f, right, we get some output. The point of an inverse is if we put that output into the inverse function, we should get the same thing that we originally put into the function. And so you can tell when we're writing something as an inverse because it'll have the letter of the function, but then it'll also look like it's like raised to the negative first power. We're not taking an exponent or anything. That's just denoting that it's the inverse. And we can find the inverse of a function like from the equation by swapping the x's and the y's and solving for y. So if I have y is equal to 3x, right, and I'll find the inverse of this. I'm just going to swap the x's and the y's. So x is equal to 3y. And then we got to solve for y. So we're going to divide both sides by 3. So the inverse is going to be x over 3. And it's important to note when we're doing this, the f of x is just another word for y. And so when we swap the y's and the x's, we're swapping the f of x's and the x's because they're the same thing. And so another way to think about it is if I am graphing some function, right? Let's say I have this function right here that goes like that. An inverse is going to be reflected across the diagonal line y equals x. So the inverse of that is going to look something like this, right? Because it's just going to be reflected. And we can't always use that for exact values, but that is just a little trick we have. All right, now this looks annoying and difficult, but I promise you it's not as bad as it looks, because all we're really saying here is you can take the inverse of like a rational function, so something that's like some function over another function. So for example, x minus 5 over x plus 3, you can take this inverse. It's just a little more complicated, so I want to go through it in a little bit more detail. So what we're going to do, so again, f of x is the same thing as y, so we can just replace that with y, right? Then we're going to swap the x's and the y's, which is what we do right here. You see the y equals becomes x equals, x minus 5 becomes y minus 5, x plus 3 becomes y plus 3. And then what we're going to do, because we're still trying to get the y on one side, we're going to multiply everything by y plus 3 because this is the denominator. So we're going to multiply everything by the denominator. So now we have x times y plus 3 is equal to y minus 5. Now we're going to multiply it out. So xy plus 3x is equal to y minus 5. And now you may say, well, this is kind of weird and random. We're not really getting anywhere. We still have a bunch of x's and a bunch of y's all over the place. And so what we're going to do here is we're going to get all the terms with y's on one side. So we're going to subtract xy to get y minus xy, and we're going to add 5 to get 3x plus 5 to the other side, right? And so we're going to get all the y terms on one side, y minus xy, and then we're going to factor out a y from here. So we have y times 1 minus x, because y times 1 is y, and y times minus x is minus xy. And so we have y times 1 minus x is equal to 3x plus 5. And then finally, just to isolate y, we're going to divide both sides by what we factored out, which is 1 minus x. So we get y is equal to 3x plus 5 over 1 minus x. And we're just going to rewrite that as f inverse. Again, this isn't raising to negative 1 power. That's just saying it's the inverse. F inverse of x is equal to 3x plus 5 over 1 minus x. So I'm going to pause. You can pause it here. Here are two functions. One of them is just a regular function. One of them is a rational function. See if you can try to figure out how to find the inverse of either one. If you can't, that's fine. I'll go over it. If not, pause the video. All right, hopefully you did at least one of those. So we're going to start with this top function because it's a bit easier. And this looks complicated, but again, we're basically just swapping the x's and y's and solving for y. You guys can do it. So again, we're gonna replace f of x with y. We don't have to do that. It's just because I like using that better. But once we got y, right, we're gonna swap that so we get x is equal to 3 times the square root of 2y minus 5. Then we're going to divide both sides by 3, right? So we have x over 3 is equal to the square root of 2y minus 5. We're going to square both sides to get rid of the square root. So we get x over 3 squared is equal to 2y minus 5. We're going to just solve that really quickly. So it's going to be x squared over 9 is equal to 2y minus 5. Add 5 to both sides, right? So we get x squared over 9 plus 5 is equal to 2y. And then finally, we're going to divide everything by 2 to isolate y. So we get y is equal to x squared over 9 plus 5, all of that over 2. And then we can replace y with f inverse of x, which is, so f inverse of x is again equal to x squared over 9 plus 5 over 2. And if that doesn't make sense, just try to go through it again, see if you made a mistake somewhere. If that does, great. It's just with this, it's a lot more intimidating than it looks. You guys can do this. All right, now what about that other one? Well, with the other one, we're going to have to use the same kind of strategy we did with the one on the last slide. So g of x is equal to 5x minus 3 over 7x minus plus 1. So first of all, you know the deal. Make g of x equal to y, swap the x's and the y's, and then we're going to multiply by the denominator, which in this case is 7y plus 1. So we have x times 7y plus 1 is equal to 5y minus 3. We solve that out. X times 7y, well, that's going to be 7xy. X times 1 is going to be x, is equal to 5y minus 3. Get the y terms on one side, so that's going to be 5y minus 7xy is equal to x plus 3. Factor out a y, so we have y times 5 minus 7x, because again, y times 5 is going to be 5y, and y times negative 7x is going to be negative 7xy. And that's the entire thing is going to be equal to x plus 3. And then to isolate the y, we're just going to divide by the remaining part again, which is going to be 5 minus 7x. And then that's our inverse. All right, now there's one more cool thing we can do with compositions, and we kind of already brushed on it, but we can use it for a lot more things. And that's because the definition of a inverse, right? Because the inverse is going to take the outputs of the original function and turn them back into the old inputs. If we compose the inverses together in either way, it's just going to be equal to x, right? Because if we think about it, x is the original input, f of x is the output, and then if g of x is the inverse of f of x, right, and it takes the output and makes it the input, g of x is going to take f of x and just make it x. And so that you can kind of see this here. If we have x and we do some function on it to make it y, well, the inverse of that is going to be make it go back to x. And so f inverse of f of x is just going to be equal to x, because you can think it's like a loop, right? If we do one function, we go from x to y. If we do the inverse function, we go from y to x. And so we can use this to prove that two functions are inverses by composing them and seeing if it all solves out to be x. So here's an example. So prove that the functions displayed are inverses. So again, you're going to want to plug one of these functions in and replace it with x. You can do either one. I think I'd do f of g of x. And so just try to see if you can do that and then get back to me. All right, now hopefully you had some idea of how to approach that. If not, that's fine. We're going to go over it right now. So again, this looks a lot more scary than it actually is. You guys can do this. But if we're replacing x in f of x with g of x, right, we're going to replace, so f of x normally is 3 times the square root of x minus 5 over 2. So basically what we're going to do is take this g of x and make x this. And so we get this absolute monstrosity of a function. And so you might be wondering, you might be thinking, oh my god, this looks so complicated, I can't solve this, this is like far beyond me. It's not, because if you notice, if they are inverses, and fun fact, they're usually going to give you functions that are inverses to prove that you can determine that they are inverses. Usually they're going to, in fact, all the time if they're inverses, they're going to have these little parts that cancel each other out. So for example, at the start, we have plus 5 and minus 5. Right away, we can cancel those out. Then we have this square, and we have a square root, and those cancel out, right? And so we just get rid of this and the square. And now we have 3 times 2x over 3 over 2. Well, the dividing by 3 and the multiplying by 3, they can cancel out. So that looks good. So then we just have 2x over 2, and the 2 and the 2 cancel out, and so we just have x. And so these are inverses. And you can also note, I didn't write it here, but you can also, if you had plugged f of x into g of x, you would have gotten the same thing, just in a different order, right? Because let's just think about that, right? If we have f of x and this is in here, well, first of all, we would have this divided by 2 and this multiplied by 2 would cancel out. Then we would have this multiplied by 3 and this divided by 3 would cancel out. Then we would have this square root and this square would cancel out. And then finally we would have this 5 and this negative 5 that would cancel out. So for there, it's going to look complicated, but as long as there's really matching things, it shouldn't be that big of a deal. You guys can do it. All right, that's it. Bye.